In order to understand what happened to our baking soda, we need to look at it from two different levels. Let's look at it at the level we can see with our own eyes, and I have that represented at the top of the screen in pictures. We start out, we have a white powder that's called baking soda. We heat it, and we don't realize this, but it's actually decomposing. To decompose means to come apart. When we're done, we have another white powder that looks very similar to baking soda. We don't know this, but that powder is actually something called sodium carbonate, and it has differently sized and shaped crystals than the original baking soda, which was much more fine, I guess I should say. We collect a gas in a bottle, which seems to be carbon dioxide. We can sort of confirm this with our splint test because we know that a flaming splint will go out when it's placed in carbon dioxide. Not conclusive for being carbon dioxide. There are other gases that might do that, including water vapor, but it does indicate to us that a gas has been formed that is different from just air. And at the top of the test tube, we see little droplets of some kind of liquid that's clear, and it's most likely that that clear liquid would be water, although we don't have any proof of this. So all we can tell by looking is that we have created a gas and a liquid and a solid that looks very similar to the solid we started with. Really, the only conclusive test that we have that shows that that white solid is a different substance and not just in a different form because of being heated is the pH test that we did with our pink chemical. When we added the phenolphthalein to it, we found that the sodium carbonate was a much darker pink than the original baking soda, which meant that it had a higher pH and that it was basic, whereas the baking soda is slightly acidic. So that's the only real direct evidence we have of a chemical change. The carbon dioxide in the water sort of imply that new substances were created, but it's hard to prove with the equipment we have in the classroom what exactly that gas is and what that liquid is. However, this is a very well-known chemical reaction, and scientists have figured out the chemical equation for it, and that's kind of what I want to talk about in the rest of this slide. In the middle, sandwiched between my pictures at the top and the bottom, you see a chemical equation. Hopefully you've seen chemical equations like this before. Probably the first one you were introduced to was photosynthesis, which looks something like this. And by the time I'm finished with you, you guys will be able to read chemical equations like this, no problem. Won't scare you at all. But right now, it's probably looking a little bit intimidating. So let me just slow down and explain to you what you're looking at. First of all, you have over here on the far left-hand side a number. And just like in math, this number is called a coefficient. Coefficient. And all it means is that there are two of whatever comes after it. Just like if you put a 2 in front of the letter x in a math equation, it means you have two x's. This means I have 2 of whatever NaHCO3 is. NaHCO3 is the chemical formula for baking soda, and the reason it has the word soda in it is because the atom sodium is in baking soda. And just to confuse you, sodium, the atom, does not have the symbol S, which would make perfect sense. The symbol S was already given to the atom sulfur, so instead we use the symbol Na, which is from the Latin word for sodium, which is natrium. Super confusing. Here's the sodium atom in the drawing down below. It's that sort of light gray atom off on the left-hand side. So there's a sodium atom, and it's attached to this big cluster of atoms down below, right here, this big cluster of atoms, is the rest of the molecule. The white guy is the hydrogen over here. Here's my little hydrogen. And the dark gray in the middle is the carbon atom. And those three red guys are the oxygen atoms, and they're all bonded to each other, which means that chemically they are one thing. They all behave as one thing. And because I have the 2 as the coefficient, notice that I have 2 molecules of baking soda. As a student in my class famously said long ago, hey, that spells nacho. Well, it almost spells nacho. He was close. The little s over here is for the word solid. It's telling you what state your baking soda is in, and we started with it in the solid state. This big long arrow is a reaction arrow, and it literally means forms or yields or becomes. So baking soda forms, yields, or becomes something else. And a lot of times you'll see written over an arrow any type of energy or any type of catalyst that you added to help the reaction happen. So sometimes we make reactions happen by heating things up, because when molecules move faster, they have more opportunity to actually break apart or come together. And sometimes we actually need a chemical to encourage the chemical reaction to happen. And this is true in photosynthesis. That's why plants are green, because they contain the chemical chlorophyll, which is necessary for photosynthesis to actually happen. You also saw that we used a catalyst when we did our experiment with the hydrogen peroxide and the black powder, the manganese dioxide. In that lab, we created oxygen gas in a bottle, and then you got to reignite it with a glowing splint. And the black powder does not actually chemically react with the hydrogen peroxide. It just encourages the hydrogen peroxide itself to break apart, and that's called a catalyst. So you often write the catalyst above your arrow, whether it's energy or a particular chemical. In this equation, we would have written just heat above the top, so that we know that we needed heat for it to happen. After it's been heated enough, the other side of the equation has what we call the products. So everything over here on the right-hand side would be known as a product. Everything on the left-hand side over here is known as a reactant. So anything to the left of the arrow is being reacted, so it's called a reactant. And everything that comes out after the arrow is a product, because it's produced by the reaction. The compound sodium carbonate looks very similar to baking soda. It's still got sodium, still has carbon, still has oxygen. And this, at least in part, explains why it looks so similar, because it has a lot of the same components. So it looks like a white powder still, although it's a little bit different. It doesn't have the hydrogen anymore. It's actually hydrogen atoms that make things have an acidity to them. So it's the loss of that hydrogen that's made our baking soda turn into a base and not an acid anymore. It's in the solid state, you see the little s, and then we produce carbon dioxide gas, G for the gaseous state, and liquid water, which actually doesn't start out as a liquid. It starts out as a gas, and then when it hits that cold glass, it condenses into a liquid and becomes visible to us. So it's released as a gas, and that's why you don't see that liquid down at the bottom of your test tube. You might have expected over here to see liquid forming in there if it was being formed, and you didn't. And this is what shocks and surprises students is, hey, it doesn't look like it's melting, it doesn't look like it's giving off a liquid, and then this liquid just suddenly appears at the top of the test tube. And that's because when it first formed, when it first broke away from the baking soda, it formed as a gas, and then it floated around in the test tube, and when it got away from the hot bottom, it was able to cool off enough, especially when it hits that glass, that it turns back to a liquid. So you can see the products look like this down here. So you have the sodium carbonate molecule, looks like this, and it has similar atoms in it, as we mentioned before. You get the carbon dioxide molecule, which looks like this, and you get water, good old water with his Mickey Mouse ears. And notice you get one each of those different products. So what we've just done is I've taken you through the very beginning of the chemistry unit, which we will actually come back to after we finish exploring properties of matter a little more. So you've just been introduced to the idea of chemistry. The idea of chemistry is that you can predict exactly what atoms are going to do when they are heated or interacted with each other. And it's pretty interesting stuff, and it will take you a long time, but you'll manage it before the end of the school year. It'll take you a long time before you get as comfortable as I am at writing chemical equations and reading them and understanding them, but I promise you will get there. But this is the very, very beginning of that process. So just to recap, because I've said a lot on this one slide, this is what I want to tell you. The important thing to get from this tutorial is that you understand, number one, that a chemical change has happened. The change that happened here at the baking soda is definitely chemical. It's important that you understand that what makes it a chemical change is that the atoms involved switched bond partners. The atoms switched who they were bonded to, forming new substances. It's important that you realize that the evidence we have for this is really only the change in pH that the sodium carbonate goes through, and that the carbon dioxide and water formation are lesser evidence. They are evidence of a chemical change, but they're not conclusive proof. So those are the important things to get from this particular tutorial. We're going to take a sharp right turn and we're going to go and look more closely at the properties of baking soda and learn how to use our lab effectively to find out exactly what the properties are of any substance. So we're going to spend some time doing that, and then we'll come back around to exploring why it is that some atoms bond to others and why chemical reactions sometimes happen and sometimes don't. So I'll see you guys in class.